Implementation of autonomous habitat systems for Mars colonization by 2030. Overview. The goal of establishing autonomous habitat systems for Mars colonization by 2030 has been outlined in a comprehensive plan that includes a budget allocation of $150 million. This plan is divided into 4 key phases focusing on robotic construction, life support systems, and communication networks essential for sustainable habitation on Mars. Key phases of development. Phase 1: Robotic construction. The first phase emphasizes the deployment of advanced robotic systems for habitat construction utilizing Martian materials. These robots will be engineered to build durable structures that can withstand the extreme environmental conditions on Mars, including temperature fluctuations, dust storms, and radiation exposure. The development of these robotic systems is critical as they will enable efficient and cost-effective construction without the need for human presence during the initial building phase. Technological advancements. Significant advancements in robotics, artificial intelligence, and construction technologies will be required to ensure the success of this phase. These technologies will include autonomous navigation, material handling, and in-situ resource utilization (ISRU) capabilities. Phase 2: Life support systems. The second phase focuses on the development of life support systems that can sustain human life on Mars. This involves creating closed-loop biospheres for air and water recycling as well as food production systems. Biosphere design. Concepts like Biosphere X and Y proposed by Martian suggest the establishment of controlled agricultural environments utilizing hydroponics and aeroponics. These systems could dramatically reduce the cost and logistical complexity of food supply from Earth. For instance, a 1-acre space farm could yield a substantial food output potentially valued at billions of dollars over decades. Sustainability. The life support systems are designed to be self-sustaining, recycling waste products and regenerating necessary resources like oxygen and water. This sustainability is crucial for long-term human habitation. Phase 3: Communication networks. The establishment of robust communication networks is essential for operational coordination and data transmission between Earth and Mars. Satellite systems. This phase involves the development and deployment of satellite systems that ensure continuous connectivity. These satellites will facilitate real-time communication, data sharing, and remote monitoring of habitats and life support systems. Data management. Advanced data management systems will be needed to analyze environmental conditions, resource availability, and the health of the biosphere. Phase 4: Testing and optimization. The final phase involves extensive testing of the constructed systems in simulated environments such as Biosphere X to evaluate their functionality over extended periods. Simulated environments. Testing will include living in simulated conditions that mimic Martian environments to assess agricultural output, environmental control systems, and human adaptability. Feedback loop. The data collected from these tests will inform adjustments and optimizations to both construction methods and life support systems before the actual deployment on Mars. Common key points. Sustainable food production. The emphasis on sustainable food production is critical as it reduces dependency on Earth-sourced supplies. Martin's projections indicate that even small-scale space farms could yield significant food value over time. Advanced robotics. The need for advanced robotics and automation is a recurring theme underpinning both construction and agricultural processes on Mars. Iterative biosphere development. The concept of developing a series of progressively advanced biospheres XYZ is vital. Each iteration builds upon lessons learned in previous stages, ensuring improvements in design and function. Timeline of events. 2024 to 2025. Focus on developing and testing robotic systems, including prototypes capable of Martian construction. 2026 Launch of Biosphere X in low Earth orbit (LEO) for agricultural testing aimed at validating the effectiveness of space farming techniques. 2027 to 2028, deployment of communications satellites and life support systems with an emphasis on integrating these technologies into a cohesive operational framework. 2029, final optimization and integration of life support and communication systems, followed by a shakedown cruise to test all systems in a simulated Martian environment. 2030, preparation for the first manned mission to Mars, leveraging insights gained from biosphere tests and robotic constructions to ensure mission success. Conclusion. The pathway to Mars colonization by 2030 is built on a foundation of innovative technologies in robotics, sustainable agriculture, and communication networks. The structured approach outlined in the 4 phases ensures a comprehensive strategy for establishing human presence on Mars. This collaborative effort across various disciplines is essential for overcoming the challenges of long-term habitation on another planet and making the dream of Mars colonization a reality. The ambitious timeline and budget allocation reflect the commitment to advancing humanity's reach into the cosmos. The aspirations surrounding Mars colonization and the establishment of autonomous habitat systems by 2030 encompass a range of technical, economic, and logistical challenges that can yield surprising insights. The $150 million budget, while ambitious, invites scrutiny regarding its sufficiency given the complexity of the required technologies and systems. Here are some counterintuitive points that emerge from the analysis of the autonomous habitat systems for Mars colonization. 1. Robotic construction feasibility. The idea that robotic systems will autonomously construct habitats on Mars may seem straightforward, however. The reality is that these robots will require significant advancements in technology and artificial intelligence that have yet to be fully realized. While it is assumed that deploying advanced robotic systems is merely a matter of funding and planning, the operational environments on Mars are vastly different from Earth, presenting unique challenges such as dust storms, temperature extremes, and the need for autonomous decision-making capabilities in real time. 2. Life support system costs. The projections regarding life support systems, particularly around sustainable food production, suggest that space farming may dramatically reduce costs associated with food transported from Earth. This expectation is counterintuitive because it overlooks the extensive infrastructure needed for farming in space, such as hydroponics and aeroponics systems, energy requirements, and the initial high costs of setting up these systems. While the potential for substantial food yields exists, the upfront investment and ongoing maintenance may negate immediate cost savings. 3. Communication network development. Establishing robust communication networks is deemed essential for Mars missions, yet the assumption that satellite systems can be deployed and made operational within the proposed timeline may be overly optimistic. The challenge lies not only in launching these satellites but also in ensuring that they can withstand the Martian environment and operate reliably over extended periods. The complexity of developing and maintaining such a network in a hostile environment is often underestimated. 4. Chronological optimism. The timeline laid out for testing and optimizing the systems, particularly with the 2-year shakedown cruise to simulate Martian conditions, exhibits a level of chronological optimism that may not align with the realities of technological development and testing. Each phase's dependencies, particularly around biosphere testing and system integration, require iterative feedback and improvements that may not fit neatly into the projected timeline. Historical precedents in space exploration often reveal that unforeseen challenges can cause significant delays. 5. Underestimated human factors. The plan to create self-sustaining habitats on Mars assumes that human adaptability will seamlessly align with technological advancements. However, the psychological and physiological impacts of long-duration space travel and habitation in isolated environments are complex and poorly understood. The notion that humans can simply adapt to life in a biosphere without significant support systems for mental health, social interaction, and physical activity might be overly simplistic. 6. Assumptions about agricultural output. The projections made by Marshall Martin about agricultural output from space farms suggest that they could yield immense value over time. However, the assumption that crops grown in non-Earth environments will replicate Earth-like productivity fails to account for the myriad of factors that affect plant growth, such as radiation exposure, microgravity effects, and potential pest or disease issues that differ from those on Earth. Additionally, the claim that even small farms could yield billions in food value is predicated on several optimistic assumptions about efficiency and productivity that may not hold true in practice. 7. Economic viability of space farming. The economic rationale for investing in space farming to reduce dependency on Earth-sourced food raises questions about the viability of such an initiative. The cost of developing and maintaining farming infrastructure in space may outweigh the benefits when considering the cheaper and more established systems of food production on Earth. The expectation that space-grown food will significantly lower costs may ignore the economic realities of food supply chains, even in a future where space travel becomes commonplace. 8. Radical growth projections. The conjecture that humanity could reach a point where more people live in space than on Earth within a few centuries presents an overly optimistic view of technological and social progress. While the vision of expanding human presence throughout the solar system is compelling, it often downplays the significant logistical, ethical, and environmental challenges associated with scaling human populations in extraterrestrial habitats. 9. Misinterpretation of manifest destiny. Drawing parallels between space colonization and historical concepts of manifest destiny raises philosophical questions about the motivations and consequences of such expansion. The idea that humanity is entitled to fill the solar system with life may overlook the responsibilities and ethical implications of altering extraterrestrial environments and ecosystems. 10. Technological dependency. The entire framework of Mars colonization relies heavily on advanced technologies that are still in nascent stages of development. The assumption that these technologies will be successfully developed, tested, and operationalized within a decade is overly reliant on a linear progression of technological advancement without accounting for potential setbacks, funding issues, or shifts in political and public support. In conclusion, while the vision for Mars colonization and the establishment of autonomous habitats is inspiring, it is essential to critically examine the underlying assumptions and counterintuitive realities that accompany such ambitious plans. The interplay between technological feasibility, human factors, economic viability, and ethical considerations will play a crucial role in determining the success of these endeavors. The report on the implementation of autonomous habitat systems for Mars colonization by 2030 outlines a comprehensive plan with 4 key phases and a budget of $150 million. While much of the content is notable, several aspects are particularly significant yet easily overlooked by many readers. Below, I highlight these crucial points and explain their importance. 1. The economic viability of space farming. The emphasis on sustainable food production in space is a pivotal element of the Mars colonization plan, specifically in Phase 2, which focuses on life support systems. The predictions made by Marshall Martin regarding the potential yields of space farming are striking. For instance, he suggests that a 1-acre farm could produce approximately 28,000 pounds of wheat per year, translating to a value of about $31.7 million if grown in space, versus the exorbitant costs of food transported from Earth. Significance. This aspect is critical because it addresses one of the most significant logistical challenges of long-term space missions: food supply. The cost-effectiveness of space-grown food could drastically reduce the financial burden of missions to Mars, which is often underestimated. The ability to produce food locally on Mars could lead to self-sufficiency, reducing reliance on Earth and making colonization more feasible. Furthermore, the economic model proposed by Martin could serve as a blueprint for future endeavors, inspiring investment in agricultural technologies that can thrive in extraterrestrial environments. 2. Advanced robotics and automation. The reliance on advanced robotics for both construction and agricultural processes is a recurring theme that deserves more attention. The report notes that substantial advancements in robotics will be necessary to facilitate the construction of habitats and the operation of life support systems. Significance. The integration of robotics is not just about efficiency, it is about safety and sustainability. Autonomous robots can operate in hazardous conditions that would be dangerous for human workers, especially during the initial phases of habitat construction. Furthermore, automation in agriculture can significantly reduce labor costs and increase productivity. This technological reliance raises questions about the future of work in space exploration and the potential for robotics to reshape human roles in extraterrestrial environments. It could lead to a necessity for new skill sets and training programs for astronauts and support staff. 3. Phased development of biospheres. The report introduces the concept of a series of progressively advanced biospheres XYZ designed for different environments and stages of development. Each biosphere aims to build upon the lessons learned from previous experiments, with Biosphere X serving as a testing ground followed by more advanced iterations. Significance. This phased approach is significant as it acknowledges the iterative nature of technological development. Each biosphere serves as a prototype, allowing for real-time learning and adaptation. The lessons learned from the operation of these biospheres can inform future designs and operational strategies, ultimately leading to more effective and resilient habitats on Mars. Moreover, it emphasizes the importance of testing and validation in space missions, a critical factor often overlooked in the excitement of exploration. Understanding the adaptability of ecosystems in space will be crucial to ensuring long-term survival. 4. Importance of communication networks. The establishment of robust communication networks in Phase 3 is another critical component that deserves more emphasis. The plan includes developing satellite systems for continuous connectivity and data relay between Earth and Mars. Significance. Effective communication networks are the backbone of any successful space mission. They enable real-time monitoring, control, and supportive operations on Mars from Earth, facilitating everything from scientific research to emergency response. The reliance on communication technology also raises concerns about cybersecurity, data integrity, and the potential for information overload. Ensuring reliable communication channels will be essential for maintaining crew morale and enabling collaboration among team members. This aspect highlights the need for comprehensive strategies addressing not only the technical requirements but also the psychological aspects of long-term isolation in space. 5. Human adaptability and long-term testing. The reports focus on the testing of systems in simulated environments, particularly the evaluation of human adaptability in Biosphere X is a crucial yet often underestimated element. The success of the mission relies heavily on understanding how humans can adapt to Martian conditions over extended periods. Significance. Human adaptability is paramount for the success of any long-duration space mission. The psychological and physiological effects of isolation, confinement, and altered gravity on astronauts could pose significant challenges. By prioritizing extensive testing in controlled biospheres, the program can gather invaluable data on stress management, social dynamics, and overall well-being. This information is vital for designing habitats that support mental health and social interaction, which are often neglected in traditional space mission planning. Moreover, insights gained from such testing can inform policies and practices for future missions, ensuring the well-being of crews as they venture further into space. 6. Interdisciplinary collaboration. The report underscores the necessity for collaboration across various disciplines, engineering, agriculture, psychology, and environmental sciences, to achieve the ambitious goal of Mars colonization. Significance. Interdisciplinary collaboration is essential for tackling the multifaceted challenges of space colonization. Each discipline brings unique perspectives and expertise that can lead to innovative solutions. For example, insights from psychology can inform agricultural designs that promote social interaction among crew members. A collaborative approach fosters creativity and adaptability, which are crucial in the unpredictable environment of space. This interconnectedness also has implications for education and training programs, suggesting a need for integrated curricula that prepare future generations for the complexities of space exploration. Conclusion. While the report on Mars colonization outlines a structured plan with clear phases and budget allocations, the overlooked elements discussed above are critical to the mission's success. The economic viability of space farming, advancements in robotics, the phased development of biospheres, the establishment of communication networks, human adaptability, and interdisciplinary collaboration all play vital roles in making Mars colonization a reality by 2030. Recognizing and addressing these factors will not only enhance the chances of success but also pave the way for future explorations beyond our planet. In-depth analysis of autonomous habitat systems for Mars colonization. The implementation of autonomous habitat systems for Mars colonization by 2030 involves a structured approach with 4 key phases. Each phase is integral to the success of the overall mission, and they collectively aim to create a sustainable human presence on Mars. Below are the 4 most valuable points for in-depth discussion and analysis regarding this ambitious endeavor. 1. Robotic construction, the foundation of Mars habitats. Key discussion points. Technological advancements in robotics. The first phase emphasizes deploying robotic systems for constructing habitats using Martian materials. This requires significant advancements in robotics, including autonomous navigation, construction methodologies, and the ability to work in extreme conditions. The challenge lies in developing robots that can operate without direct human oversight and respond to unforeseen conditions on Mars. Material utilization. Utilizing Martian regolith as a primary building material is crucial for reducing the need for transporting materials from Earth, which is cost prohibitive. This phase must explore techniques like 3D printing with Martian soil to create habitats capable of withstanding Mars's harsh environmental conditions, including extreme temperatures and radiation exposure. Infrastructure development. The success of the entire colonization effort hinges on creating reliable infrastructure. This phase must address the design and construction of not only living quarters but also essential facilities such as laboratories, greenhouses, and energy production systems. 2. Life support systems, ensuring human survival. Key discussion points. Sustainable biospheres. The second phase focuses on developing life support systems to create sustainable biospheres. This involves advanced agricultural methods such as hydroponics and aeroponics, which can produce food in a controlled environment. The feasibility of these systems must be evaluated through prototypes like Biosphere X, which will be tested in low Earth orbit (LEO) to simulate Martian conditions. Resource recycling. Effective life support systems will require closed-loop systems that recycle air, water, and waste. This is crucial for long-term missions, as resupplying from Earth will be infrequent and expensive. Research must focus on integrating biological and mechanical processes that can efficiently recycle resources. Psychological and social factors. The human element is paramount in long-duration missions. Life support systems must not only provide physical sustenance but also address psychological well-being. This includes creating social spaces, maintaining communication with Earth, and ensuring mental health support for crew members. 3. Communication networks, bridging Earth and Mars. Key discussion points. Robust communication infrastructure. The establishment of reliable communication networks is essential for operational coordination and data transmission between Earth and Mars. This phase involves the development of satellite systems that can ensure continuous connectivity, allowing for real-time data sharing and decision-making. Latency challenges. Communication with Mars faces inherent latency challenges due to the distance between the 2 planets. Solutions must be developed to mitigate the effects of communication delays, such as autonomous systems capable of making decisions locally or employing predictive algorithms to anticipate issues. Integration with Earth systems. Communication networks must be integrated with existing Earth-based systems to facilitate support and resource management. This integration can enhance mission efficiency and provide a fallback for critical operations. 4. Testing and optimization, ensuring system functionality. Key discussion points. Simulation and testing. The final phase involves extensive testing of all systems in simulated environments like Biosphere X. This phase is critical for assessing the functionality of life support systems, agricultural outputs, and environmental control systems over extended periods. Testing must encompass both technical performance and human adaptability. Iterative design process. An iterative design process should be employed where feedback from tests informs improvements. This will require a flexible approach to system design, allowing for adjustments based on real-world performance data gathered during simulations. Risk management. Establishing a robust risk management framework is essential for identifying potential failures and developing contingency plans. This includes evaluating the reliability of life support systems and communication networks and ensuring that backup options are available. Conclusion. The implementation of autonomous habitat systems for Mars colonization is a multifaceted endeavor that requires a concerted effort across various technological and human factors. Each of the 4 key phases, robotic construction, life support systems, communication networks, and testing and optimization, plays a vital role in ensuring a sustainable human presence on Mars by 2030. By addressing the challenges and opportunities within these phases, humanity can take significant strides toward becoming a multiplanetary species. 1. The Apollo Program 1961–1972. The Apollo program was a pivotal space exploration initiative conducted by NASA, aimed at landing humans on the Moon and bringing them safely back to Earth. Its most famous mission, Apollo 11, successfully landed astronauts Neil Armstrong and Buzz Aldrin on the lunar surface on July 20, 1969. The program consisted of several phases, including extensive robotic missions Apollo 4, 5, and 6 that tested rocket systems and spacecraft in low Earth orbit before proceeding to crewed flights. The total budget for the Apollo program was approximately $25.4 billion, equivalent to about $150 billion today, showcasing a significant investment in technology development, including life support systems and communication networks crucial for lunar missions. 2. Biosphere 2, 1991–1994. Biosphere 2 is an ecological research facility located in Arizona, designed to replicate Earth's environmental systems. It served as a testbed for understanding closed ecological systems vital for future space colonization. The first mission involved sealing a crew of 8 inside the biosphere for 2 years, 1991–1993, to study human survival and agricultural practices in a controlled environment. Despite challenges such as oxygen depletion and food production issues, the project provided valuable insights into life support systems and sustainable agriculture that can inform future Mars colonization efforts. The lessons learned from Biosphere 2 are directly applicable to the phases of constructing autonomous habitats on Mars. 3. The Mars Society's Mars Desert Research Station 2001–present. The Mars Desert Research Station (MDRS) is a research facility established by the Mars Society in Utah to simulate Martian living conditions. The station has hosted numerous crews of researchers and volunteers who live and work in an analog environment, conducting experiments related to habitat systems, agricultural techniques, and human factors. This initiative aims to prepare for long-duration missions to Mars by testing life support systems, communication networks, and sustainable food production in a controlled setting. The MDRS operations are a practical representation of the testing and optimization phase in the proposed Mars colonization strategy, providing real-world data on human adaptability and resource management in isolated environments. These historical cases exemplify the exploration of autonomous habitat systems, showcasing technological innovations, ecological sustainability, and human adaptability in extreme environments, paving the way for future endeavors in space colonization. Future outlook: autonomous habitat systems for Mars colonization by 2030. The ambitious plan to implement autonomous habitat systems for Mars colonization by 2030 is a multifaceted endeavor that involves advanced technologies, sustainable practices, and international collaboration. With a budget of $150 million allocated across 4 key phases, this initiative aims to establish a permanent human presence on Mars through robotic construction, life support systems, and robust communication networks. Below are predictions and insights regarding the future of this project. 1. Robotic construction 2024 to 2025. Predictions. Advanced robotics. By 2025, we can expect significant advancements in robotics, particularly in the areas of autonomous navigation, material handling, and construction methodologies. Robots will be able to utilize in situ resources (ISRU) such as Martian regolith to construct habitats, reducing the need for materials transported from Earth. Collaboration with AI. The integration of artificial intelligence will enhance robotic capabilities, enabling real-time problem-solving and adaptation to the Martian environment. This will facilitate more complex tasks such as assembling multi-component structures autonomously. Future impact. The successful deployment of robotic construction will lead to the rapid establishment of basic habitats, significantly reducing the initial logistical burden of sending materials from Earth. By utilizing local materials, costs could be minimized, allowing for more funds to be redirected towards other critical areas such as life support and communication. 2. Life support systems 2026 to 2027. Predictions. Sustainable agriculture, biospheres targeting sustainable food production through hydroponics and aeroponics is projected to be operational by 2026. This will enable the cultivation of essential crops in a controlled environment, minimizing reliance on Earth-supplied food. Closed-loop systems. Development of advanced life support systems will focus on closed-loop ecological systems where waste is converted into resources. Technologies for oxygen generation, water recycling, and nutrient recovery will be key components. Future impact. A self-sustaining food supply will enhance crew morale and reduce operational costs associated with food transport from Earth. Successful implementation of life support technologies will pave the way for human adaptability in extraterrestrial environments, increasing the feasibility of long-term missions. 3. Communication networks 2027 to 2028. Predictions. Global communication infrastructure by 2028. The establishment of a dedicated communication network, including satellite systems in orbit around Mars, will facilitate continuous connectivity. This will enable seamless data transfer between Earth and Mars, critical for mission coordination and scientific research. Real-time data exchange. Enhanced communication capabilities will allow for real-time monitoring of habitat conditions, agricultural outputs, and crew health, enabling rapid response to potential issues. Future impact. Robust communication networks will not only support colonization efforts but will also serve scientific missions, enabling data collection and analysis from Mars's surface. Increased communication capabilities could lead to collaborations with international space agencies, fostering a global approach to Mars exploration. 4. Testing and optimization 2029 to 2030. Predictions. Simulated environments. Extensive testing in simulated environments such as biospheres will commence in 2029. This phase will evaluate the functionality of life support systems, agricultural outputs, and the overall adaptability of human crews. Iterative improvements. Insights gained from testing will lead to iterative improvements in habitat design, agricultural practices, and life support technologies, ensuring that systems are reliable and efficient before actual deployment on Mars. Future impact. The knowledge gained from these tests will be invaluable for preparing for the first manned missions to Mars scheduled for 2030. It will not only validate the technologies but also refine operational protocols for long-duration space missions. Successful testing will instill confidence in the viability of Mars colonization, potentially leading to increased funding and support for future missions. Conclusion: the pathway to Mars colonization by 2030 is structured around the strategic implementation of innovative technologies and sustainable practices. The four key phases: robotic construction, life support systems, communication networks, and testing are interdependent and critical for establishing a human presence on Mars. As advancements in robotics, agriculture, and communication technologies evolve, they will significantly contribute to the feasibility and success of this monumental endeavor. The potential outcomes of this initiative extend beyond Mars. They could serve as a blueprint for future human settlements on other celestial bodies, marking the dawn of a new era in space exploration. Moreover, successful colonization efforts could foster international collaboration and propel humanity toward becoming a multiplanetary species, fundamentally altering our relationship with space.